So with this bell work, I initially thought B and it's not B, I'll tell you that. And I thought that because for me, it was because I didn't read the question correctly the first time around. And then I went back and I saw the answer and I was like, oh, okay, I just didn't read it right. So hopefully that's what you guys discover as well. So we got a botanist running a test. She has 40 plots. So I'm going to think of it this way, where you've got 40 plots split into 4 parts, and it says half of them are in sunny locations, half are in the shade. So I'm going to say that these right here are all in shady locations. And then the next one, it says she selects 10 sunny plots and 10 shady plots to use for one fertilizer. So this is going to be fertilizer 1, and this will be fertilizer 2. So it actually does appear as though I misread it because I only read this sentence right here. And I was like, wait, she allows for sunny and shady for one of them, but the other doesn't say anything about. Well, it doesn't have to say anything about it because it's kind of understood that the other two are going to be split evenly as well. So actually sun is controlled for, so it's not confounding anything. So anything involving sun, so that one is not correct. The sun here in the water won't be confounding either. So what's going to be confounding is the fertilizer in the water, because what happens is the fertilizer requires different amounts of watering. So if fertilizer 1 requires more watering than fertilizer 2, then we're testing two different things. We're testing two things at once. We're giving different amounts of water and we're giving different amounts of fertilizer, or different types of fertilizer. So really what's benefiting the plants? Is it the water amount or is it the fertilizer? And we're confounding it. So we need to control that. There's your correct answer, A. Okay. And there we go. That's basically it. So we're going to be looking at the last kind of significance test, but luckily it's mathematically, it's the same as other stuff we've done, which we'll see very shortly. But it is kind of a switch in how we interpret a question. And so we're looking at paired data. And that's what we've got going on. So researchers designed an experiment. We're going to start by constructing a confidence interval, but we're going to look at significance tests as well. So they're designing an experiment to test study the effects of caffeine withdrawal. And I think this might actually be set up as a test, but we're going to make it into a confidence interval. It doesn't matter. Each subject was barred from coffee, colas, anything with caffeine for a certain amount of time. Then during one 2-day period, they took capsules containing their normal caffeine. Another 2-day period, they took placebo capsules. Then the order in which the subjects took caffeine and placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression at the alpha equals 0.05 significance level. So we're actually going to change this problem. I screwed this up a little bit. We're going to construct, instead of this, and we could come back to this and do the actual hypothesis test, but we're going to construct a confidence interval for this. So we'll go with a 95% confidence interval for the change that someone might expect, being off of caffeine. Okay, higher scores show more symptoms of depression, so higher scores are not good. Now, here's what we mean with paired data, and hopefully it's just immediately obvious, is that we had one test subject right here who had 2 different measurements related to him or her. And so for every one of these test subjects, they all have paired data, kind of the data with a caffeine and with a placebo. And we want to compare those two. And there's a natural way of comparing. Now, if I want to compare that to like a random thing, if I took a sample of tires, I don't know why that keeps coming up as just an example in my head. I don't know. But like if I was going to compare the quality of tires and I just picked, you know, X number of tires from one company and then X number of tires from another company and compared the two to see which one had higher quality. Now I can't naturally say, oh, well, here's all my tires from company A, here's all of them from company B. I can't say, oh, well, this one naturally pairs with this tire. And this one naturally is going to pair with that tire, so these two will pair also. I can't do that. This is basically these are two independent samples that you wouldn't pick any two of them in particular to pair together. We just say, you know what, I got a big old group of tires. I'm going to get the average, maybe average tread life, and I got another one over here. I'm going to get the average tread life over here, and I'm just going to compare those means because that's all I can do. But the difference, of course, here is that with this stuff up here, I can actually say, I'm going to compare the placebo results for subject one to the caffeine results for subject one. I can do a natural comparison. Okay, so hopefully, and we'll re-emphasize that point more, but I just wanted to initially bring it up. So what I want to do is I want to create another layer right here. You don't need to copy this down, certainly, but I do want you to maybe have these numbers down. So I'm going to come up with the difference, and I'm going to go ahead and do it as placebo minus the caffeine, just to keep it consistent. And I'll probably end up with more positive numbers that way. So if you like to end up with positive numbers, then you can always kind of look into it that way. So 16 minus 5, this is the placebo minus the caffeine here is going to give me 11. That's the difference. 23 minus 5 is 18. 5 minus 4 is 1. So, okay, we can just go through. I'll write down what we've got. And I ended up right here because I'm keeping it consistent. My very last one is actually a negative 1. I'm going to do placebo minus the caffeine. That can happen. There's nothing wrong with it. So at this point, this is the data set that I'm going to work with. Okay, and what I want to do is I want to construct a confidence interval about how much change might we expect in depression level, you know, based around this test. How much change might we expect for the average person? That's really kind of what we're solving for when we do a confidence interval. Okay, so anyways, let's see here. I don't need to worry about this data up above at all anymore because for the rest of it, I'm only working with the differences, and I'm going to create a list in my calculator, obviously, and I'm just going to plug this data in. So for my list, I've got 11, then 18. So make sure you're plugging this data in too so you can calculate as we go through. And once I've plugged the data in, we need to calculate our one variable statistics. I'm kind of jumping a little bit ahead, but we have to do this anyway, so we could do it at the beginning. All right. So I got 7.364, however much precision you want to go out to. There were 11. Okay, and I'm going to come back to this and explain a few things, but then I got 6.918. Hopefully you guys got the same thing. If we didn't, I might have made a mistake. Okay. So we only now have one sample really that we're dealing with, which is the differences for each subject. It's one sample. So this is gonna be very similar to a one sample t-test. Okay, that says one sample t-test. It's gonna be very similar to it, but it's not that exactly. This is gonna be our paired sample t-test, because we're starting off with, again, 2 measurements for each person, and we're just looking, or whatever the subject is, but in this case 2 measurements for each person, and we are getting the difference, and we're doing an analysis on the difference, the list of the differences. Okay, now we're going to have some different terminology. First of all, N here is going to be the number of pairs. So of course, each person has two data points associated with them, but there's 11 people, so that's why N is 11 here. And when we're talking about X bar, it's not just X bar of a data set, it's X bar of a data set of differences. So I'm going to refer to this as X bar diff. I'm just going to put DIFF as a subscript. And for the sample standard deviation, it's the differences. I'm going to add sub diff right here. And hopefully it follows that if we are working with the sample mean for differences and the sample standard deviation for differences, then we're using this to estimate the parameter of the population difference, or the population mean of differences, which here is going to be the true mean difference in depression. And I could put placebo minus caffeine. The statistic that we're using to estimate it, we already calculated. I'll just put it up here. X bar sub diff, which is going to be 7.36. Oh, can't write. 364. There it is. And our confidence level for this is going to be 95%. Okay. So hopefully, and for the first part of this, I want you to just focus on understanding the process. If you're still a little bit hazy on, wait, when do we use this method and when do we use a 2 sample t-test? Because that's going to actually be the big thing. I want to make sure that's clear right now. The big decision you're going to have to make is, when do I do a 2 sample t-test and when do I do a paired samples t-test? So you have to decide between these two, and here we're in a paired sample. And again, hopefully the logic behind it is clear enough for right now, but again, we're going to come back to it. So let's move ahead there. No, went too far. The name of this procedure, I will erase some stuff here. I'll try and keep my data. Okay. So there we go. The name of this procedure is the paired sample T interval. So we're still working with means, so we still have a T interval, but now we're dealing with paired sample, and the conditions are pretty much the same. We need to make sure that it's random, that 10% condition is met, and that it's normal. So random, is it random? It looks like there was randomness in how they assign things. The random, and the idea is that we want this to be representative. There were some volunteers. So, I think generally speaking, okay, so this is random as far as people being diagnosed as caffeine dependent. Okay, so as long as we only generalize this to that group, then this is random enough. We can't generalize this to the entire population, but only those as being caffeine dependent. 10% condition, did we meet it? Well, I'm going to assume more than 110 people in the world are caffeine dependent. So that's good. And then normal, we did not get 30 in our example, or in our sample size. So now we need to assume that the population is approximately normally distributed. And we just have to make that assumption. They don't give us information that says that, at least not that I can read. So we just would say it's normal because we're assuming, and this is pretending to right, we're assuming that the population is approximately normally distributed for, for the variables of interest. Okay. So there we go. We checked our conditions. Now I know sometimes it seems like I blow off these checking conditions, but remember you do need to show it. And it is important that you give a justification for it. I just kind of verbally talk through it sometimes, but make sure that you are doing that. So now we can actually do the calculations. And here's where things get a little easier for us, okay? Compared to the 2-sample t-test. All right. So our general formula is for any test, or sorry, for any interval, sorry, I keep saying t-test, t-interval. For any interval, it's going to be the stat plus or minus the critical value times the standard error. Okay, so our specific formula, now this is where we might be a little bit confused. So what do we use for standard error, critical value, all that fun stuff? But it's actually just going to be the same as though we were constructing a confidence interval for one sample mean. So if we think back to that, we normally had X bar plus or minus a T star critical value times S over the square root of N. All right, so our standard error is S divided by square root of N. So now the only thing we need to change about this is that now we're dealing with X bar sub diff, and this is S sub diff. And that's it. That's it. That's the only change we have to make. But we've already calculated those values by using one variable statistics. And so this, hopefully you're like, oh, okay, this is really easy calculation. I've already practiced this. I know what I'm doing. So really it's not that big of a conceptual leap at this point. So the work, I'm going to plug the stuff in. I got 7.364 plus or minus my T star. This is where things get really nice. But actually, I'll come back to that. My S diff, I'll just plug in 6.918 divided by the square root of 11. This is my sample size. So our degrees of freedom for something like this is just going to be n minus 1 again. So it's going to be the number of pairs minus 1. So in this case, it's 10. So we go back to a very simple degrees of freedom calculation. No complexity to it in any way, shape, or form. Now, I don't have my table B pulled up, but I know I'm working with a 95% confidence level, and I have 10 degrees of freedom. Can anyone find, real quick, what the critical value is for 10 degrees of freedom with 95% confidence? And I'm double checking on my calculator, but I want you guys to be able to look it up. Okay, 2.228 is the critical value. Very good. Hopefully you guys, if you didn't go to table B and look it up, hopefully you know what to do in order to find it. 95% would be your column. You go up until you get to 10 degrees of freedom, and then you can look at what that value is. Now you can get this on your calculator as well if you remember how to use inverse T to get that, all well and good. Otherwise, no big deal. The table is actually maybe your better option for this kind of stuff. So anyways, let me plug it in, 2.228. We've gotten all the values we need. Now it's just straightforward solving. So I will find the margin of error first of all. All right, and I got 4.647. You guys can just compare your calculations against what I'm getting. Okay.
What numbers do you plug in to find that for inverse T?
Inverse T, I did 0.025 because you have to remember that you have 2.5% on your lower tail and upper tail. So 0.025 for the area and 10 for degrees of freedom.
Okay, thanks.
All right. And of course, when you do that, you'll get a negative number, just everyone out there. The negative doesn't matter when you do that, so just take the absolute value. Okay, so that's the confidence interval that we've created. So this tells us that the true average change that someone's going to experience among people who are caffeine dependent when they don't have caffeine is they're going to feel depressed somewhere between 2.7 and 12.011 according to this test. So it looks like more symptoms of depression. Okay, I guess that's a sign not to get dependent on caffeine or always have caffeine available. You know, you can choose how you interpret those results. All right, so I'm going to clear everything so I can say that we are 95% confident that the interval from 2.717 to 12.011 captures the true mean number of symptoms of depression that a caffeine dependent person will exhibit when deprived of caffeine. And I didn't phrase that exactly right, so I'm going to add something to it. The true mean number of symptoms of depression that a caffeine dependent person will additionally exhibit, because they're going to show maybe some signs on their own, but this is going to say how many more. Okay, and that's one of the central ideas behind this method, is that we're not saying there's going to be some absolute, like, let me say it this way. The variation that each person experiences should be in this range, but the absolute amount of, symptoms of depression that someone experiences will depend on how many they might have had to begin with. Like if we come up here, test subject number 10 already started off with 11 signs of depression or symptoms of depression just while having caffeine. And so when they lost it, they went up one, So they still showed an increase. But then you come over here to number 7, they had no signs of depression and went up to 6. Down here, even kind of more extreme, this person had 5 symptoms, but jumped up to 24, and that's the highest number. So this person is a real caffeine dependent person. So we expect the average person, or on average, people are going to show somewhere between 3 and 12 more signs of depression than they would have otherwise. So the variation within a person is going to be more than the variation in absolute numbers. And we'll see that more in a different example. All right. So are there any questions on this process? Okay. So now I wanted to go through another example, of course. Now we're going to be doing a significance test. I could have done a significance test on the last one, but we'll just run through this. And we've got different data. Now we're looking at, okay, we got 10 cars that are all going to be given regular gas and allowed to use up their tank. And then they were given premium gas and allowed to run through their tank. And basically, the miles per gallon that they got for each type is going to be compared. Now, it was randomly determined which one they got first. So there's some randomization going on. And I think maybe the first thing that I would do before I jump into any of this stuff, I mean, I would want to identify, you know, in my mindset, the first thing I want to identify is there a natural comparison where one data point should be compared to another data point and only that one? So it doesn't make sense for me to take this 26 and compare it to the 21 right here, because those are 2 different cars. If I could just compare anything to anything, then that would be an example of a 2-sample t-test. But here, there's only one natural thing to compare this 26 to, and that's to the 25. So if I only have one possible data point to compare this to, that's telling me it's a paired samples. Okay, so I'll just put paired. That's the one we're doing, not this one. So hopefully, yeah, hopefully the idea behind it's clear enough. All right, so if I've already satisfied myself that I'm looking at a paired samples problem and I'm going to be doing a t-test for it, then I'm going to find the differences. And I want to do, just because positive numbers are better to work with in some cases or in some people's mind, I'm going to go with premium minus regular. So that it looks like if I look across at the data points, it looks like I'm going to get positive numbers for the most part. 19 minus 16 is 3. Okay, I won't say all of them out loud, I'll just write the answers. There we go. That did not show up. There it is. So always doing premium minus regular. Now I can put that in as a list and run my one variable stats. I'm just going to put this right here. And I'm going to let you guys fill this in when you get that done. Okay, very good. Something's going wacky here. So there we go. We have the sample standard deviation for our differences and the sample mean for our differences. I'm just going to add the 4 right here at the end. Okay, so now we can look at, let's just kind of start this process. If this is kind of how practically I would approach it, I'd be like, let me get all my stats. And then I'll kind of worry about showing the proper method. All right, so we did that. We have the numbers we need to proceed. The parameter we're going to be estimating is mu sub diff, which is going to be the true mean, okay, whatever. That says mean difference in miles per gallon. And I'll just put premium minus regular. Okay, the statistic I'm going to be using is x bar sub diff, which is 2. Significance level doesn't say, so I'm going to use a 0.05. And I'll just put alpha equals 0.05 and hypothesis. Okay, so this will be hopefully something that you would expect. Since we're trying to figure out mu sub diff, what would our null hypothesis be? Maybe let me ask it this way. What would a no change scenario look like for this problem?
It would be the same as the mean of regular gas.
All right, so premium wouldn't give us any increase. There would be no difference between them. So the upshot of all this is that our mu sub diff for the null hypothesis is that it's 0. We're saying there's no difference between them. And no matter how many miles per gallon you get to begin with, you're not going to see an increase. So, of course, our alternate hypothesis is that our difference will be, I'm going to say greater than 0. And the reason I say greater than 0 is because I'm doing premium minus regular. So I would expect if premium really does give us more miles per gallon, that when I subtract the regular away, I should see a positive difference. Okay, so that is it. Pretty straightforward. And remember, if I had ended up with mostly negative numbers because I did regular minus premium, then I would have said my mu sub difference is less than 0 for the alternate hypothesis. Okay, so we can do some of this. I'll just erase rather than clear the page. All right, takes a little bit more time to do this, but no big deal. All right, so name of procedure. This is going to be a paired sample t-test. I just did a paired sample t-interval. Now it's a t-test. The conditions, random. Let's see, we've got 10% and normal. So the random here means that can this be generalized? You know, if we're generalizing this to the fleet of cars for this company, because maybe they all drive a certain way or have to drive in certain conditions. So if we generalize this, then I think these 10 cars that they picked, we could consider a random sample. And of course, there's randomization in how they assign the treatments, in what order. 10%, I will assume that there are at least 100 cars in this fleet, in this company fleet. Now, again, sometimes you just have to make assumptions. And I just want to emphasize again, if that was the case on an AP test, I would want you to write out a sentence. I sometimes get lazy, and so I don't always set the best example, but just to cover all your bases, you would want to say, it doesn't explicitly say these were random cars, but we will assume that they are. Okay, and that covers your bases right there. 10%, it doesn't say how many cars are in the fleet, so we will assume they have at least 100 cars, and therefore we met the 10%. Normal, we certainly didn't meet n is greater than or equal to 30 because we only have 10 in our sample. So now we're going to say, for our assumption, we will assume that the differences that they get, all the differences are normally distributed. So the differences we calculated here, we'll assume they're all normally distributed. Again, so if you write that out, if it doesn't give you explicit reasons to believe that it is, and you just write out your assumptions, then you've covered your base and you're good to go. Okay, so now we can do the calculations, what we've all been waiting for. I'm going to go ahead and clear the page. Hopefully you have those numbers. So the general formula for a significance test is the stat minus the parameter divided by the standard error. Now, the standard error for, and we already talked about this, for a one sample t-test, would be s divided by the square root of n. But here, the only difference we make is that it's s sub diff. So we had to first of all find the differences, then we could plug that into our data set and get all the numbers. So the mean is going to be, well, the mean that we're searching for, the population mean, is, we're assuming, going to be 0, because that's our null hypothesis. So they're really talking about the parameter here, but we also have our x bar sub diff. So anyways, so now let me kind of plug in, create our specific formula, which is x bar sub diff minus mu sub diff divided by s sub diff divided by the square root of n. All right, now I'm going to have a page that has these formulas on it. So if you come back to the presentation later, you'll find it. But of course, it's a good idea to be following along, copying this stuff down. But you can see it's a pretty straightforward calculation at this point. I don't have the numbers anymore, but I do know that my x bar sub diff was 2. The mu sub diff is 0 because of the null hypothesis. S sub diff was 1.414, and the sample size is 10. So now I can run through those calculations, nothing to it. Okay. Hopefully you had time to calculate this on your own, come up with the same number I got. And remember, because we're dealing with means, our test statistic is a t-statistic. So that means we're not dealing with a normal distribution, we're dealing with a t-distribution. And if I have my mean right here, then I'm going to be 4.5 rather, standard deviations away. There's 1, 2, 3, 4, 5. I'm going to be sitting somewhere about here. So showing something in your diagram, of course, we could be more specific and we could show that this is, standard deviation of 0.447. And we could even show the numbers and everything like that. I'm being a little bit lazy with it, but we're showing the diagram. I think we're explaining ourselves clearly enough to show that if this is our t statistic, we're looking for this right here, which is the p-value. So anything that extreme or more, so will be the p-value. And I'm sure you guys can all tell there's going to be very low probability of happening. This is certainly going to be statistically significant, but let's get the exact number. And our calculation for that is going to be TCDF. For those of you with the interface, you can figure out your lower and upper bound. I know at least one person here has to plug it in just using comments and everything. So remember, our lower bound will be, since we're going toward positive infinity, my lower bound will be the 4.474. Upper bound will be, we could just say 99. And our last parameter to plug in is going to be the degrees of freedom. If we have 10 as our sample size, my degrees of freedom is going to be 1 less. That's 9. And there it is. We can calculate that. I got 0.00773. Okay. So there's only a 0.08% chance of getting this kind of a result by random chance, assuming that the null hypothesis is true. So we can reject the null hypothesis. Okay. I'm going to move to the next page. If there are any questions, you can jump in. And now we'll conclude. So I really hope as we keep going through these significance tests, this process is you're like, oh, it's this again and this again. Because, yeah, we're just kind of repeating it. You can see where I mentioned, and hopefully it's very much clicking now because this is the last significance test that we have for means and proportions. It's just taking those same ideas from first semester and just plugging them in a different way, creating a different recipe out of it. Now we can conclude this one. We can say because I can never write on iPads. Because the p-value is less than the significance level, and I'll put 0.000773 is less than 0.05, we reject the null hypothesis. There is convincing evidence that, and before I just start writing stuff, I want to scour the problem to see if there's a good way of phrasing this. So many drivers of cars that can run on regular gas actually buy premium in the belief that they will get better gas mileage. So there is convincing evidence that buying that premium gasoline will result in better gas mileage. So again, we're looking at the prompt that we were given. We are replying with our answer in the same terms, basically. And just as a quick aside, when I was in college, I took a statistics class, and it had to do with medical geography and stuff like that. And we were looking at all kinds of different results. And every single time we would run like 20 tests in a row. Every single time my professor insisted that you use the same format like 20 different times. You had to write 20 sentences. And I was like, oh gosh, it's very redundant. Because the p-value is blah, 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 that means that blah, 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 blah. And you just have to say that over and over and over again. So I'll say it's just good statistical practice, even if it gets redundant, okay? And that eliminates any ambiguity in someone who might misinterpret what you're trying to say. So is there evidence that cars get significantly better fuel economy with premium gasoline? Yes, we do have some evidence of that. We had a statistically significant result showing that that's the case. All right. How big might that difference be? Check a 90% confidence interval. Okay. So I want to do this quickly. We've already run our checks for inference, and we already have the data. So I'm just going to do the calculation, which is x bar sub diff plus or minus the critical value times the standard error. All right, so this is going to, I already started plugging stuff in and then I stopped. So we'll just start with stat rather. All right, so it's going to be t star times s divided by square root of n. This is s sub diff. All right, so knowing these numbers already, I want to figure out, okay, great. And this is maybe where we can see the benefit of a confidence interval versus a significance test. So I just proved that there is a difference between regular and premium gas as far as miles per gallon go. But how much might we expect to get improvement? So X bar sub diff is going to be 2 plus or minus my S sub diff is 1.414 divided by the square root of 10. Now for the T critical value, you can go to your table and look at the 90% column, go up until you find 9 degrees of freedom. Alternatively, you can do your inverse T in your calculator. It's going to be a 0.05 area with 9 degrees of freedom. And however you look it up, you should get 1.833. So I'll just finish doing the calculations real quick and write them out. Okay, wanted to give you guys some time to look at that and go through and hopefully come up with the same confidence interval that I did. So at this point, we can say that it's statistically significant that we're going to get a change, but we can look at it right here and say that the change is just going to be basically from 1 to 3 miles per gallon more for using premium. Okay, I'm not writing out my final statement, but I'll just verbally say it. We are 90% confident that the interval from 1.18 to 2.82 captures the true mean difference that a person might get for in miles per gallon for using premium versus regular gas. I'm not sure I like exactly how I phrased it, but you get the idea. So the next question, and this is obviously a textbook problem. So this right here could be like the last question on an FRQ. So even if the difference is significant, why might the company choose to stick with regular gasoline?
Because it's cheaper.
It's cheaper. And is it a major improvement in miles in fuel economy?
Not like too huge.
Right. I mean, if you could get 10 more miles per gallon, or maybe not even that much, if you were like sitting between 4 and 6 for your confidence interval, you could run the math and you could figure out, think of, just to kind of fully answer this question, you'd have to keep in mind that greater fuel economy means you have to fill up less. You have to use fewer gallons. So if my gallons go down over the course of the year, but the cost goes up, then I have to kind of multiply that together. How many gallons might I expect times the cost? And if I use the other one, regular gas, where it's more gallons per year, but at a cheaper cost, if I multiply those together, if this is greater than that, then that means it costs more, even with the fuel economy savings. So this is why you might still stick with regular gas. It comes down to economics. I mean, I think it's obvious enough as an answer, but you can make it more mathematical. Okay, so this is something, we're not going to actually run this analysis, but suppose you had done a bad thing and you had considered this as a difference of means, a 2-sample t-test, and you took that, and you got X bar sub 1 and X bar sub 2, and you ran it through your 2-sample t-test. Without running through the full mathematics behind it and calculations, it would not be statistically significant. And the reasoning behind it is, notice that from one car to the next, whenever we created our differences, we got basically consistent numbers, okay? And that shows that we are consistently getting some results. But within each group, if I consider like this X bar sub 1 group, the regular, there's a lot of variation there. It goes down from a low of 16 up to a high of 28. Premium goes from a low of 19 up to a high of 32. There's a lot of variation there. There's not very much variation when we get the differences, okay? So the fact that we have so much variation means that this turns out not to be statistically significant in a two-sample t-test, and the variation in the within the groups hides the differences that are there when we compare one to itself. I don't know if the phrasing of that worked very well for you, but it all has to do with the amount of variation. So when you can naturally compare one result to another and only to one other, then you want to use paired t-tests. Okay. Might call that good for now and wrap this up. So here are the formulas that we were using. So if you didn't already write them down, they're right here. Not much to it. So this is really, I should say this is our test statistic. I should have a t equals right here. But good. We're good with that. You can always come back and look at that later. So this is kind of to come back to that idea of how do we decide to use a two-sample t-test or a paired t-test. And so there are some different ideas, not just what I'm about to show you. We're going to go through like 3 slides of this. How many samples do I have? If I really only have one given, then it's going to be mean of differences. Okay, and I'll come back to that. If it's 2, then of course we're going to be looking for probably the difference of means. So I want to make sure this terminology is clear. When we talk about a difference of means, I've got X bar sub 1, and I've got X bar sub 2, and I'm taking a difference there. So that's the two-sample t-test is going to be 2 means, and I'm taking the difference between them. But a mean of differences is I got a whole data set full of differences, and I'm going to get the mean of it. So X bar sub diff is a mean of differences. So you might see either one of those terms. And I know it's kind of confusing. It's just like type 1, type 2 error, keeping those straight. So you're going to have to think through difference of means or mean of differences. All right. So this first one, that one's kind of iffy for me. I got this online. Can any piece of data in the first group be compared to any piece of data in the second? And if so, then it's going to be a difference of means. And so that's like if I took a sample of, I threw out tires earlier, but, or did I? I might have done that 5th hour, I don't know. But if we had a sample of, you know, components from one corporation and I want to compare them to components of another corporation, I wouldn't say this component right here has to be compared to this component right here, and that's a natural pairing. There is no natural pairing, so any piece could be compared to any piece, which means I'm using a difference of means. But if they must stay in pairs, because there's only one natural pairing, then it's going to be a mean of differences. Do they reference pairing the data? Okay, so obviously if it just says there's paired data, well, that makes it easy for you. You're using paired t-test or t-intervals. So, depending. So the definition in the textbook, I think, also helps to illuminate this a little bit more. The first 2 sentences especially. So data are paired when the observations are collected in pairs or the observations in one group are naturally related to the observations in the other. The simplest form of pairing is to measure each subject twice, often before and after treatment is applied. So we saw that with the caffeine pills. So we did 2 different measurements. Okay, so good there. And kind of the last thing to think about is just ask if the observations are independent of each other. So if data was collected before and after treatment, then they're not independent of each other, and therefore you might say that they're not independent, so that you would use the paired t-test. Because the before and after a treatment is kind of dependent on the input and the person who's receiving the input, the treatment. So paired t-test. But if they're all independent and you can't directly pair in individuals in one random sample with another, that's a two sample. Okay, so the last little bit right here, we're gonna do something like we did yesterday. I'm gonna give you guys just a few problems and I want you to circle if it's gonna be a paired t-test or a two sample t-test. So let me clear right here. All right, pretty straightforward. I'll leave it up for you. Okay, we've got a couple of responses here for paired t-tests, and this does make sense. If I'll just say, I know they talk about 20 divers, but here's diver 1, 2, and 3. I don't want to compare the new flipper versus the old one. I don't want to compare this data point to this one. There's a natural pairing right here, new and old for each person. So paired t-test. So it makes sense to pair. All right, very good. So pretty quick answers on this one. And obviously a white piranha from a decade ago and a white piranha from this decade, like which one do you compare to which? There's no natural pairing. This is a two sample t-test. Okay, good job. All right, I will let you guys look at this one now. Okay, this is definitely one that is a little bit trickier for you guys to think through it. And we want to think, so we've got different, so we've got, let's see, old wetsuit or the new wetsuit. And we've got 16 times, so 1, 2, 3, 4, ... 14, 15, and 16. So it's going to be randomly assigned. So I'm going to, you know, I'm going to use the old wetsuit for the first time period, and then I'm going to do the new one for the next two, and then back to the old. And it just so happens that the last three all happen to be the new wetsuit. So the question is, which one would you naturally compare this result to? To the 12th time period? To the first time period? To the fourth time period? Is there a natural pairing here? All right. So I threw that out as a rhetorical question, and the answer is really, this is kind of a tricky one, but it turns out that this is a two sample t-test actually, because we really just are collecting data of two different types, but we're not pairing it with, there's no natural pairing between this particular trial and this particular trial right here. So we wouldn't say, oh, these two must match up, and there's no way we can compare this one to anything else. I could compare this one to this one if I wanted to, and it would be just fine. Okay, so hopefully that's making more sense, you know, in retrospect. Okay, so next one. Okay, so the idea is paired t-tests, and this caused some confusion with some students earlier. I think because it might not be clearly labeled, but it is a paired t-test. So just to answer this one right away, you're right. So this would be, you know, our 6 students. And of course, there's a natural way of comparing how they did, how this student did in August versus how they did in June. And we can compare all of these, you know, to the one, you know, compare the student to him or herself. So there is a natural pairing. It's a paired t-test. At this point, I would want to create my new row here of differences. So if I did June minus August here, it'd be 4, and that'd be like negative 16, negative 6, that'd be positive 2, that'd be negative 6, and that'd be negative 10. So if I did my math right with all that. So anyways, we would just proceed that way. I'm not going to run through the whole calculation, just kind of get us started. Okay, very good. I think this is the last one. Okay, we've got a consensus building around 2 sample t interval. Again, that makes sense here. Boy number 3 wouldn't naturally be compared to girl number 3. He could, if you wanted to compare him to girls, you can compare it to any girl you want, you know? So there's no natural pairing here. And there you go. Because there's no natural pairing, what we want to do is take all these values, come up with our x bar sub 1, take all these values, come up with x bar sub 2, and of course s sub 1, s sub 2, and n sub 1, n sub 2, all that fun stuff, and do a 2 sample t interval. Okay, so a little bit of new stuff thrown out, but the calculations really are repeats of the 1 sample t test and t interval. Different ways to think about some stuff today, but hopefully you're walking away from class feeling like it's not too much added. Here's your homework. I want to draw specific attention to some progress checks that are available for you. 6C, 6D, and 7C are going to be the multiple choice questions that are going to resemble ones on your test on Monday. So I highly recommend you run through those. Pretty soon, I'm going to be marking down zeros for people who haven't been doing the progress checks. I've been not doing that so far because they're not due till the end of the semester, but I want to keep you guys aware of what work needs to be done. So your homework is right here. In your homework, you're going to have times where it is a 2 sample t-test or a t-interval, and sometimes it's a paired samples t-test or t-interval. So you're going to have to read it and make sure, and when you check the back of the book, you can double check which one it was supposed to be. Okay, that's it. If you have questions, stick around. If you're good to go, enjoy your weekend, and I'll see you on Monday.